So take it easy. So today is we switch topic to something quite different. So there's no spin grid here. It's all like a spin orbit and quantum criticality physics. So before I do that, I would like to make an advertisement. Probably some of you already heard about this. In 2020, like two years from now, maybe 1 year and a half from now. So there is a conference called the International Conference on Highly Frustrated Magnetism. So this conference is held every 2 years. So this year, 2018, it was in UC Davis, California, United States. So in 2 years, and 1.5 years, it will be in Shanghai. So Professor Xiaoqun Wang from here and Professor Xiang Tao from LP, Beijing, and Professor Fu Chunzhang from Cambridge Institute of Theoretical Science in Beijing. So and me. So we managed to convince the international organization committee to have this conference in Shanghai in two years. Yeah. So just to give you a advertisement. Yeah. Today's talk will be so has four parts. So the first we give some introduction to spin-1 quantum magnets. Just very broadly explain why spin-1 quantum magnets is interesting. So then I switched to more specifically to spin-1 degrees of freedom on a diamond lattice antiferromagnet, and then give you a few two theoretical insights to explain some thought about this compound, or more generally on 3D transition metal oxides. So this work, so first I wrote a paper by myself, then has a collaboration with Dr. Fei Li, who is sitting in the audience somewhere. So yeah, it's a preprint here. So yeah, let me start from this spin-1 magnets. So in 2016, there was a Nobel Prize awarded to Duncan Haldane for his theoretical discovery of spin-1, Haldane phase, Haldane gap, spin-1 has change. Yeah. So in the early 1980s, he had some theory paper try to understand the physics of spin change, half integer spin change and the integer spin change. He found that there is a key difference between half integer spins and the integer spins. Half integer spin in one dimension, is gapless, and spin-1 change, he found it should be gapped. It's a topological effect. The gap is a topological effect. Yeah. So he did everything in terms of mapping into a nonlinear signal model and found that there's a Berry phase effect and the Berry phase effect is different for spin-1 half change and the spin-1 change. For spin-1 change, the Berry phase is completely gone, and then the system is equivalent to nonlinear signal model and should be gapped. Right? So later on there is a paper by these four peoples, AKLT. So A means Affleck, so Ian Affleck. So the rest of them I don't remember. So they construct an exact wave function for a model they wrote down. So this exact wave function is a wave function for spin-1 degree of freedom. So in this wave function, so each lattice site composed of two spin-1 half degrees of freedom. So these two spin-1 half degrees of freedom, so you symmetrize them, you form a total spin-1 degrees of freedom. So but then these two spin-1 half degrees of freedom, so they're not paired among themselves. They form singlet with another spin-1 half from a nearby spin-1 composite. So these blue link means it's a spin-0 singlet. It's an antisymmetric spin-1 singlet. And this circle, this elliptic circle is a symmetrized version of this spin-1 half degrees of freedom. You form total spin-1. So this wave function is the exact solution for Hamiltonian that constructed by AKLT. These four people. So this is called AKLT state. It turns out AKLT state, is in the same phase as this spin-1 Heisenberg chain that was proposed by Duncan Haldane. So they are in the same phase. So
we're talking about Heisenberg chain is the X model. I mean,
it's a Heisenberg model. Yeah, Heisenberg model. It really doesn't matter. If you deviate from Heisenberg model, still you can have this Haldane phase.
If it's deviated from Heisenberg model, it doesn't mean it's.
Yeah, I'm talking about spin-1 chains. Okay. Yeah. So this is the AKLT state is in the same phase as Duncan Haldane. This Haldane phase. So this state is one example of actually topological phases. The bulk, the bulk is gapped. If you cut the chain, so there is always unpaired spin-1 half. In this case, there is one paired one spin-1 half degree of freedom that is unpaired here, and there is another one here. So this effective spin-1 half that emerge out of a spin-1 interacting spin-1 system is rather non-trivial. So this is an example of bulk edge correspondence. Anyway, so later on, I'm just introduce some history. So in 2012, I think 2011 or 2012, is a very beautiful work coming out of Xiaogang Wan's group. So he and his collaborators, so they managed to make a systematic classification using beautiful mathematics called group cohomology to understand the interplay between symmetry and topology, so-called symmetry protected topology phases for bosonic degrees of freedom in various dimensions. So he obtained these symbols, these tables. What does this table really mean? So for people who have never seen this, this is a symmetry of a system. For example, if we take this U1 symmetry, just means this bosonic system has some conservation law. Has this global U1 symmetry. The system is invariant under global U1 rotation. So for SO3, that means the system has this global SO3 rotational symmetry. For instance, for the spin-1 integer spin degrees freedom, on a lattice, it will have SO3 symmetry. It's not SU2. SU2 is a subgroup. SO3 is described as integer spin rotational symmetry. So that's the symmetry of the system. For different symmetries, so this is called a semi-direct product. So that means it's not. So this time also Z2 symmetry. If you apply that, it will impact on this U1 phase. So that's the difference between direct product and indirect semi-direct product. So this is the symmetry of the system. This is the dimensionality of the system. So they managed to classify all possible symmetry protected topological phases in different dimensions. So these Z2 means there are two different kind of SPT phases. Z1 just one. Z just then is integer copies of SPT phases. This tells you how to read these tables. So this is really a great advancement of theoretical physics, theoretical condensed matter physics. So in last 1 decade or more than 1 decade, there was huge activity in the topic of topological insulators. So that the well-known topological insulator is actually a fermionic SPT, a free fermion SPT without any interaction. So that is protected by time reversal symmetry. So on the surface of topological insulator, there is a time reversal symmetry protected Dirac cones, all number Dirac cones. So if you introduce time reversal symmetry breaking on the surface of Ti or in the bulk, so the surface protected, the time reversal symmetry protected Dirac cone will be gone immediately. So this is different from symmetry enriched topology order we talked about yesterday. So this is symmetry protected topology phases. So if you destroy the symmetry, the phase is destroyed. In the case we mentioned yesterday, if you remove the symmetry, the phase still persists. So it's different. Yeah. So the symmetry here is a crucial element to generate this topological property, topological phases in the system. So through Xiaogang and his collaborative work, so we understand that this topological insulator is forming SPT, and this AKLT Haldane state is another spin SPT. It's a SPT in one dimension. It's a it's a boson SPT. Spin degree of freedom is bosonic in nature. So as we know, like for bosons, if there is no interaction, just a free boson hopping on lattice, boson will always condense and form superfluid. So to prevent boson from condensation, one has to introduce some kind of interaction to stabilize some non-superfluid phases for the bosons. So as a result, in order to physically obtain bosonic SPT, bosonic symmetry protected topological phases, one has to have a strong interaction between the bosons to prevent the boson from condensation. So then come to the very important question. So what's the physical mechanism for the SPTs, for the bosonic interacting SPTs? So which physical system could potentially realize bosonic SPTs? So that's a
in a conventional sense, like in PI, usually people can calculate certain numbers to classify different topological states. So is there any connection between, the meaning under this group cohomology and the meaning between that?
No, I actually don't know. I don't know. So when you talk about Chen number, you know the model, you know the Hamiltonian. Here we don't even know the Hamiltonian. So this is mathematical classification. So there's not even a physical looking Hamiltonian yet.
Yeah, because this is really a many body view function of the ground state.
Yeah, this is mathematics. This is.
Does this tell we never get a non-billion order?
This is different. This is not really. This is not a topological order. This is symmetry protected topological phase. So this is like a system has a short range entanglement. Topological order has, by definition, should have long range quantum entanglement. It's completely different phases. So there is no so-called emergent non-locality in this case.
Even for short range interaction, it can still lead to long range entanglement. There's no
Sure. I'm saying short range entanglement, not saying short range interaction.
Okay.
So this is different from this topological order. Topological order then is described by topological field theory. There is a fractionalization. There is anionic statistics.
Yeah.
Here you don't have it. Here is topological phases. There's nothing like that. It's different. Just be relaxed. There's nothing. So the question, the really important question is, now this style is quite different from conventional condensed matter physicist style, condensed matter theorist style.
I still remember in a 2013 summer school in Princeton, Nicholas Reed pointed out that at that time, Shanghai is also there. Really say that this classification somehow has some error inside. So it's no.
I don't know. Then some people claim they find some.
Actually, Shanghai admit that there's an error inside.
Yeah, and some people claim they find some more SPTs beyond the group cohomology. So later on, Xiaogang revised his classification, try to include this beyond the group cohomology example into some.
When you do the group cohomology, you make everything to be a billion.
I'm not interested in this. Let's just continue with that. So I think this is great. Theoretical advance. Try to converge the different topics in condensed matter. Originally, who knows the connection between topological insulator and this Haldane spin one change.
Like I read that, okay, for example, let's write down a very simple quantum Pfeffer model, like 3 plus 1. Then, does that mean for this field theory, ground state also has certain this kind of topology? Or?
It can be trivial. So this classification means, for Z2, one is non-trivial, the other is trivial. Right. So just like a Z2 classification for the topological insulator.
Trivial in what sense?
Trivial, there is no surface state. There is no surface, this bulk, non-trivial surface bulk correspondence. So like a topological insulator, if the Z2 invariant is a trivial one, then surface is completely trivial. So this classification, for Z2, that includes both the trivial one and the non-trivial one.
But I know, for quantum Pfeffer model, 3 plus 1, high energy guys have been working on them more than 50 years. So
Well,
it's hard to say it's trivial or non-trivial. So.
Yeah, let's not be obsessed with this. But
Okay.
yeah. So yeah. So this new understanding bridge this topological insulator with spin one Haldane phase. They realize that they belong to the same kind of some kind of physics. So the real one of the actually most important question in the field would be, find a physical example. We are doing physics. This is so find the first step would be, can one write down a physical looking Hamiltonian? Physical looking Hamiltonian means some interaction can be potentially realized in reality. Can one write down a physical looking Hamiltonian that give you a ground state of SPT kind, interacting bosonic Hamiltonian? So actually, Shanghai and his collaborator actually make several contributions in that direction. But I don't think there's any conclusive result. So the other direction is, can we find a physical system that can potentially realize SPTs? Right? So Shen Center from MIT, who is a colleague of Xiaogang Wen. So he and his student and postdocs, they put forward a paper, try to answer this question, right? Try to address these issues. So in this paper, the title is Topological Paramagnetism in Frustrated Spin 1 Motor Insulator. Let me explain this notation. Some nomenclature can be quite confusing for people who are not in the field. So he and his collaborator invented a notion called the topological paramagnetism or topological quantum paramagnet. So this name is a bit confusing. So paramagnet really means the system do not really order. Usually we learn in condensed matter physics. Paramagnetism means in a magnet, when the temperature is high, there is no magnetic order. So if you apply a magnetic field, there is a polarization being induced. So that's a paramagnetism. So there is no permanent magnetic order. So he add a topological in front of that to use this name to describe boson spin SPT, symmetry protected topological order with topological phases with spin degrees freedom in high dimension in 1D or 3D, 2D or 3D. So so in his name, so the Duncan-Haldane phase would be a spin SPT, spin topological paramagnet in one dimension. Yeah. So they propose a frustrated spin 1 quantum paramagnet are natural setting for realizing such tests in 3D. So the idea is that they try to find, the motivation is they try to find time versus symmetry protected SPT, with spin degrees of freedom in high dimension. Yeah. So that's the goal. So they actually propose the frustrated diamond lattice model. Appears to be this is a suggestion, not really a proof. So they suggest that maybe a frustrated diamond lattice with spin 1 degree of freedom in 3 dimensions. So such as the spinel compound material, manganese aluminite and cobalt aluminite, which belong to the general families of material of form Ab2O4. So they try to suggest a diamond magnet may or can potentially be a candidate for spin SPT in high dimension. Yeah. So that was a suggestion, not really a proof. So later on, in 2017, there was a APS March meeting abstract by people from Johns Hopkins, the Tyler McQueen, who is a material scientist who makes various materials, magnetic materials. So he proposed this material, nickel rhodium oxide, where the nickel ion form a diamond lattice, so hosting a spin 1 degree of freedom. So he proposed that they try to make connection between their experimental findings with the theoretical suggestion that spin 1 diameter lattice can realize SPT. So they quoted recent theoretical work suggests that spin 1 on a diameter lattice would enable a novel topological paramagnetic state generated by fluctuating Haldane chains within the structure with topological protected end states. Right? So comparison with to the theoretical models indicate that this system might fulfill the requirement necessary to have both highly entangled and topological behavior. Yeah. So that's the really the existing data they have is some thermodynamic measurement. So they didn't find the system really develop a magnetic order. So the system remain non-ordered, down to very low temperature from the heat capacity and magnetic susceptibility measurement. And moreover, the system has a tetragonal distortion. Yeah, so that's a summary of the no experiment from their work. So it's a spin 1 magnet with a diamond structure and a nickel ion. So in this system, the nickel ion form a lattice called a diamond lattice. So this is the lattice in the actual diamond when the carbon form this kind of structure. Here in this material, nickel form this kind of structure. So nickel ion, they arrange themselves into a pattern, which is a diamond pattern. Yeah. So this is the information of the lattice. So in addition, the system remains disordered down to 0.1 Kelvin, and the system has a cubic to tetragonal distortion around 400 Kelvin. So that's the experimental fact. Right? So then let's try to understand the experiment to see whether the system really supported this topological paramagnet or not. Whether this is just a simple speculation or a reasonable suggestion, right? So then we can carry out some kind of theoretical modeling to understand the physics, right? So let me just quickly go through the second part of work by myself. Then I come to the work with Feiye. So this is the diamond lattice. So this is a spinel structure. The nickel is occupy A site. So the A site is this the center of this tetrahedral. They form this diamond lattice. If you take all these A sites out, this form this A site. So the relevant for the magnetic system, the relevant degree of freedom comes from the spin degree of freedom for this nickel ion. So there's the nickel ion. It has it's atomic physics, really. It has 8 electrons, nickel 2+. It's a motor insulator. The charge is, you don't worry about the charge degree of freedom. So there's only spin degree of freedom. You put 8 electrons over here. So imagine, so the T2, so this is in a tetrahedral environment. So T2G levels is higher than EG levels. So you feel the EG level completely and partially feel the T2Gs. And if you imagine, because of this tetragonal distortion, the T2G is not really degenerate. There is no threefold degeneracy. So the T2G will split among themselves. And EG also split because of this tetragonal distortion. So after the distortion, imagine the system, the T2G levels are arranged in this fashion. So you put 8 electrons over here. So 4 of them occupy the lower EG and 4 of them occupy the upper T2G. So the upper T2G will give you a total spin 1 local moment. So that's what will be a total spin 1 local moment on a diamond lattice. So diamond lattice is a bipartite lattice. Bipartite lattice is just like a square lattice. You can label A and B sublattices. So if you only consider near stable interaction for the on the diamond lattice, there is no interesting phases. The system just ordered in a nail fashion. So you don't worry about, there's nothing interesting there if you only consider force neighbor interaction on diamond lattice. Just like if we consider nearest neighbor Heisenberg interaction on a square lattice. So nothing is interesting over there, right? So to get something interesting, you need to introduce some frustration. So the frustration is included by photon level interaction. So if you add a photon level interaction, which is second level interaction, which is indicated by this arrow. So this so diamond lattice is a bipartite lattice. It's also has two sublattices. The Bravais lattice of diamond lattice is the FCC lattice. So this green color and the blue color, they indicate two different sublattices. They
so for nickel iron, so the outer shell electron is 8.
is 8.
But if for nickel iron, then it's fully occupied.
It's D10, right? It's
then it's fully
D10.
occupied.
Yeah, it's D10. Yeah, you take 2 electrons, you get a D8. Yeah. Yeah, so this so the green and the blue represents two different sublattices. So the J1 would be the interaction it's an intersublattice interaction. It's the interaction between two sublattices, and J2 would be the interaction within the same sublattices. So each sublattice is an FCC lattice, right? So if you don't know much about the geometry, so a Heisenberg model on a bipartite lattice will simply favor a antiferromagnetic Néel state, right? For J2 Heisenberg model on a FCC lattice, which describes the interaction within the same sublattice, will favor line degeneracy in momentum space. So if you combine these two together, you will get a huge degeneracy in momentum space, then the spiral degeneracy, then the surface degeneracy in the momentum space. So I'm just saying, in order to obtain some new physics, some interesting physics out, we'll have to introduce for the level interaction on top of the near stable Heisenberg model, right? So that seems to be enough, but there is an extra new thing, which is this single ion anisotropy, and this is allowed by symmetry. This is because of this distortion. This cubical to tetragonal distortion occur at 400 Kelvin. So if you go from cubical to tetragonal, so the cubical symmetry is gone. So ABC direction is no longer equivalent. So ABC is no longer equivalent. So C direction or Z direction will be different from the in-plane direction from AB direction. So you immediately single out the Z component of the spin. So this thing is allowed by symmetry. Moreover, this is spin 1 degree of freedom. There is more Hilbert space. There is a larger Hilbert space than spin 1/2. For spin 1/2 degree of freedom, this thing is constant. You don't worry about it. So for spin 1/2 degree of freedom, there is not such a term. So only for spin 1 degree of freedom, you can have that, right? So that seems to be the complete Hamiltonian. So one immediate experimental consequence for introducing this term is so if you measure, susceptibility, Curie-Weiss temperature along different apply field along different direction, you obtain different Curie-Weiss temperature. So you can confirm this if you have single crystal samples. And so everything has an experimental consequence. Everything we write down would have an immediate experimental consequence. Some of them is not obvious, but takes time to explore. So let's see what we can do to this Hamiltonian. So as I said, without this term, just focus on the J1, J2 model with spin 1 degree of freedom on a diamond lattice. Actually, some people have done some very nice work with classical Monte Carlo, assuming the spin are classical. Spin 1 and spin 2 can be large. You can ignore the quantum fluctuations. Just consider, Heisenberg interaction, classical Heisenberg interaction, do a numerical separation. So they found, the system actually forms some kind of spin spiral state. Spin spiral is it means if you follow a direction in a lattice and trace the direction of the spin. Spin is a vector. So this spin, if in different sides along this direction, actually rotates. Here will be here, at this side will be this, and the side will be that. rotated in a plane. So the way how it rotates, along this direction will organized by a wave vector, a momentum, a propagating wave vector called Q. So this is a so-called spin spirals. Spin spirals are described by a phase variable that describe just like a light, just like a spherically polarized light, right? Left polarized light and right polarized light. There is a propagating wave vector and Q and omega. So they describe how this electric field and magnetic field are rotated as the light is propagating. So as this spin, as you follow this direction in the lattice, the spin is a vector is also being propagating. So there is a wave vector Q describing how the spin is propagating. So it turns out for J1, J2 model on a diamond lattice, this propagating wave vector Q is not unique, right? It's not just one or two or discrete number. It's actually a macroscopic amount of Qs. So this macroscopic amount of propagating vector, they all give you degenerate energies. They give you the same energy, and these Qs they form a surface in a Brillouin zone. So this is a three-dimensional Brillouin zone of a FCC lattice, of a diamond lattice, and this sphere or this surface formed by all these Qs. But all these Qs are not. They are at the mean field level, at the kinetic level, they give you the same energy, but really they're not equivalent. By equivalent means they are equivalent under symmetry. You can go from one to the other by a symmetry operation, either lattice symmetry or time reversal symmetry. But here it's not. They are not equivalent. Some spots, are more active than the other spots. So these hot spots are preferred by either thermal fluctuation or quantum fluctuation. So the system will prefer some certain spots. These are marked as green colors. So as you cool the system down to very low temperatures, they develop various magnetic orders. So there will be a hot spot along one direction. This spot. And at this point, at this different J2 over J1, you get another 1 point around this circle, right? So they will keep it evolve. Yeah. So the way how the system selects all these degenerate spirals on a degenerate surface is a factor called order by disorder. It's ordering due to thermal fluctuation. Naively we would think thermal fluctuation would destroy order, but it's not the case, right? Thermal fluctuation will give you a correction, give an entropy correction to your free energy, right? So your free energy will be different for different momentums on the surface, right? So then you find the smallest free energy one. So then you find the ordinary wave vector. Similarly, quantum fluctuation can also do that. So at the mean field level, at the classical level, all these momentums on the surface give you the same classical energy, but they have different quantum zero-point fluctuation. So what is quantum zero-point fluctuation? This is what we learned in quantum mechanics. For a simple harmonic oscillator, so what's the ground state energy? The ground state energy is 1/2 h bar omega, right? So the excited energy will be n plus 1/2 h bar omega. So for each mode, there is 1/2 h bar omega. This is quantum zero-point energy. So for every ordinary wave vector, for every spin spiral, which tell you how the spin are arranged in the system, they have different. They have their own fluctuation mode. Each fluctuation mode will have this 1/2 h bar omega. So if you sum all these 1/2 h bar omega for different momentums in the Brillouin zone, it will give a total quantum zero-point energy. So quantum zero-point energy for different momentum should be different, unless they are related by symmetry, right? So as I said, the degeneracy here is due to fluctuation. It's not due to symmetry, right? Degeneracy can come from a couple of reasons. It can come from symmetry. They are degenerate because of symmetry. So then you can only if you remove the symmetry, you can remove the degeneracy. But the degeneracy here is due to symmetry. It's accidental. It's accidental symmetry. It should not be protected. Any perturbation can lift this degeneracy any other fluctuation can lift this. Fluctuation can lift the degenerate too. So quantum fluctuation, which appears as total 0-point energy, can lift the degeneracy and favor various order. So that's the thought behind our work here. So in our case, so this is a quantum phase diagram. So how do you think about this? There are a couple of ways to. There are two different ways of thinking about this this phase diagram. Depends on how you look at this model. So you can go from down to from top to bottom or from bottom to top. So let's go from the up down approach. Up down approach. So this axis is the axis of single ion entropy. This dz term. This axis is the J2 over J1 axis. Right? So in this, when this term is dominate, forget about this. Forget about this. Just think about this. This is a non-interacting single ion term. So if this sign is positive, the ground state is immediately null. It's a trivial quantum paramagnet. So the ground state will be SZ equal to 0 on every side. It's a trivial simple product state. So there is no entanglement, nothing interesting. It's a trivial state in the limit when this term is very large, right? So that describe the wave function in this limit, right? So now you slowly decrease this if you're going down, and you slowly decrease in single ion entropy and introduce exchange interaction. So then this state is gradually being destroyed. And
strange. Why dz divided by J1 plus 3J2?
Yeah, this is the ratio. The QEY's temperature is proportional to this term. Okay? So you should use this as a measure of energy scale. Right? Yeah. So if you go down, so this quantum paramagnet is being gradually destroyed, and you will induce magnetic order. So this phase diagram basically illustrates the competition between a single ion entropy and the super exchange interaction. So the exchange interaction will favor some kind of order, order of some kind, and the single ion entropy will favor a trivial simple product state, S equal to 0 on every side. So there is a competition between them. The competition between them lead to some kind of quantum critical behavior. Yeah. So that's a top-down approach. You can study the instability. You start from this state, which is very well understood, right? So you start from this state and study the instability of this state. Once you destabilize this state, you introduce something new. You find something new out of by destroying this state, you obtain magnetism. So you go from this state to this state by destroying this state, by studying the instability of that. Right? That's the way. That's one approach. Right? So the other approach we don't need to we don't need to worry about we don't need to understand this quantum paramagnet phase. Try to understand the instability of that. We can just start from this axis. We can just start from this axis. Try to understand the physics on this axis. So this is interacting spin 1 degrees of freedom in a diamond lattice. We can do mean field calculation and introduce quantum fluctuation to understand how the system obtain magnetic order. So this is the other approach. You can just focus on the magnetism. So that give you understanding what's going on over here. Yeah. So this one can combine these two different approach to obtain this the complete phase diagram here. Yeah. So this is some calculation we did. If we start from this quantum paramagnet, we map the spin to some, spin 1 is special. You can map into rotors with a bosonic rotor, with a U1 rotor, and you examine how the rotor become, how they condense, essentially. You can actually work out all the excitations in this quantum paramagnetic phase. So this state, as I said, is completely trivial. It's nothing topological. It's a trivial paramagnet. It's a trivial quantum paramagnet. It's not a topological quantum paramagnet. Right? Yeah.
This is the mean field treatment.
Some kind. Well, in the limit it's not, right? Yeah. Yeah. So this is a different kind of mean field treatment. The mean field, different mean field is designed for different physics. Yeah. So we map into rotors and look at the instability of these rotors, use coherent state partial integrals, and to work out the excitation spectrum of the system. So we found you can find for different ratios of J2 over J1. So for different ratios of J2 over J1 in this quantum paramagnetic phase, so you can obtain the excitation. So the ground state is a completely trivial state, which is mostly connected to this trivial product state. Because this is in the same phase, even if the actual wave function strongly deviates from this trivial product state in the limit when d is very large, but you can mostly deform the wave function from here to here. So there is no phase transition. So it's connected to a trivial state in the limit when dz is very large. Yeah. But the excitation is non-trivial. So this is the excitation spectrum for different ratios of J2 over J1. So this is the energy. This is the momentum. So this is cut in the kx ky plane. Kx ky plane. Fix the kz component. Then you plot this energy dispersion. You find the spectrum has a as you evolve J2 over J1, the spectrum has extensive degeneracy, the minimum of the spectrum. So the excitation has some dispersion. The dispersion has some minima. The minima means the energy, the lowest energy part of the dispersion. Then the degeneracy of this minima. And
dispersion.
Huh?
The ring dispersion.
It's like a ring dispersion. But this is a cut in the kz equal to 0 plane. So if you build all these kz planes together, this degeneracy form a surface, right? So there is a surface degeneracy. So if you plot these surfaces, that's for different ratios of J2 over J1, you form this. So the degenerate minima of the bosonic excitation form a degenerate surface in the Brillouin zone. So this is rather non-trivial, right? So imagine if you close the gap of the excitation. So the system has the excitation is fully gapped. There is a gap between the zero energy and this degenerate minima. Okay? So if the system approach, if the system approach this phase boundary, all these minima, all these degenerate minima, they will condense at the same time. They become critical at the same time. So this is a completely different type of criticality. So it's not like a conventional 5-4 theory or Gaussian theory, a multi-component Gaussian theory. There are discrete number of bosonic modes become critical. So here, all these modes on the bosonic surface, this is not Fermi surface, it's bosonic surface, they become critical at the same time. So this is different. This is similar, a little bit similar to the Fermi surface. On the Fermi surface, there is a lot of gapless modes on the Fermi surface, and give you constant density of state. Right? In this case, all the degrees of freedom, all the excitation are bosonic. So as the system approach to criticality, all these bosonic modes on the bosonic surface become critical at the same time. So it will give you a constant density of state. So you get most likely you get a T-linear heat capacity. So it's different from simple Gaussian theory in 3 + 1 dimension. You get a T cubed heat capacity and corrected by with a logarithmic correction due to fluctuation, right? So here you get a T-linear due to the very large density of states, due to the constant density of states from the critical fluctuation on the.
In mean field theory, the dispersion is linear or quadratic in K.
No, it's so.
Long wavelength limit.
No, it's
I mean, if we respond to the theory around a certain minimum point, you always have a certain dispersion.
No. So along the tangential direction. So this is like a Fermi surface. This is flat, right? Along this direction, it's a linear dispersive, right? Along these two tangential direction, it's not, right? Just like a Fermi surface, if you do tangential direction expansion, you don't get a linear dispersion only along this direction.
So in that case, can we claim that along this direction, the interaction is marginal, but in this plane, the interaction will be relevant? And how can it be stable against the interaction?
Now here I'm not considering. No, I don't understand the question, but
Because eventually, because it's a mean field, right? Eventually, you need to include the interaction and see how the interaction.
Yeah. So if you go to very low energies, eventually the degeneracy will be broken. You will select some hotspots. Yeah. Some hotspots will be selected.
Due to the interaction.
I think due to not just due to interaction.
Because you along this direction, the perpendicular direction.
No, it's not due to interaction. It's due to the do some other, just like how we select the ordering within the order first. It due to quantum zero-point energy fluctuation will select some of the hotspots.
That would be strange because if your claim is correct, along this direction is linear. Now along this direction, interaction should be marginal. However, along this plane,
No, I'm not considering very long distance low energy physics.
Because you are talking about low energy excitation near the
right.
the new surface, still low energy, right?
Right.
So in this case, we still can consider how the interaction will come into play. And then along this plane, then the interaction will be strongly relevant because it says flat, it's flat band. So it's hard to imagine the interaction plays a fundamental role here.
Yeah, so that will be very low energy physics. So I'm not want to do that. So the claim is if you at low, not very low energies, you would find the constant density of states that give you this T-linear heat capacity. Yeah.
But usually, if we didn't consider the very low energy, the mean field, in most cases, in my mind, almost break down everywhere. In many
I'm not interested in field theory. I'm not really interested in
theory.
Yeah.
It's about like in real material, like eigenmagnetics or some other material. If we try to apply the mean field theory to a node that small energy scale, then usually the theoretical prediction deviate from the experimental data very strong. So that's one way I think you need to justify.
It's okay.
Because when you carry a mean field, usually you already do certain average, right? Like because when you consider the commute relation between the phase and the particle, and then you already assume the phase is already become very smooth fluctuation. Or else, this commute relation will break down because there's no way to make a data file become infinitely larger. Because in your commute relation, you already can lead to data file times data n is equal to h divided by 2. Then you assume that data file can be very large. But in your case, you already assume that data file must be very small because we know the phase fluctuation cannot go beyond 2 pi. So then in my understanding, your theory already is a low energy theory. It's not certain in the middle energy scale.
No, it's not a low energy physics. So at the low energies, if you go to very low energies, as I said, this degeneracy is not protected by symmetry. So they're not equivalent. They should not be equivalent. So there's no reason they have to be equivalent. So they are degenerate only in a proximate sense. So if you are serious, right? If you are very serious, so there are always other perturbations in the Hamiltonian. Will prefer some hotspots in the energetic reason. Just some certain level interaction will do that. But I'm not really interested in that. If you go to very low energy physics, you need to worry about other perturbations in the system. Will lift the degeneracy. Will prefer some one direction hotspots, and then the physics will be described by the very low energy excitations around the hotspots. Yeah. Yeah. So I'm just trying to understand the consequence of frustration on the excitation spectrum. So people in the field mostly focus on the consequence of frustration on the order itself, not interested in the consequence of frustration on the excitation spectrum. So here, this is the huge degeneracy in the excitation spectrum is a consequence of frustration. The degeneracy of the spectrum, not degeneracy of the classical mean field ground state. Right? So that's a pretty interesting thing. As the system approaches to the ordering, all these modes become essentially critical. So so that's the all the understanding, right? These all the understanding, and in this within this order regime, it's the quantum zero-point energy that selects the ordered pattern, due to quantum zero-point fluctuations. So that's the second part. Using the rest of time, I want to advertise some very nice work with Fayet, Dr. Fayet. So as I said earlier, so under the tetragonal crystal fields, the EG is lower than T2G, and due to the tetragonal distortion, so the T2G is no longer degenerate anymore. So there is no threefold degeneracy over here. In the previous part, I assume XY is lower than the XZ and YZ, such that there is no orbital degrees of freedom. So if you put the XY above this XZ and YZ, just like case for this iron by semiconductors, iron selenium, so there is the actual orbital degeneracy here. So there are two different ways how you can place the 8 electron on such a energy levels of crystal field. So that will give you a twofold orbital degeneracy. In fact, it turns out that this entropy measurement in the system find the entropy is actually above the pure spin 1 magnetic entropy. So pure spin 1 magnetic entropy is R log 3, right? So there is the actual entropy due to orbitals, which is log 2, right? Add them together is R log 6, right? So this actual entropy is due to the orbital degrees of freedom. So the orbitals are actually active here. So when you consider the active orbitals, so you need to worry about the coupling between the spin and the orbitals. So for partially filled T2G shells, one has to always worry about this, especially when T2G is degenerate. Now we assume T2G is degenerate and put the 8 electrons over here. So the T2G is partially filled. So now, if you do this, if you think this way, there are threefold orbital degeneracies. Although the angular momentum of T2G is L equal to 2, but if you fill 4 electrons, or effectively fill 2 holes, four electrons like fill 2 holes, the total orbital angular momentum works as effective spin 1, effective L effective equal to 1. So L effective equal to 1. And from simple Hans rule, S equal to 1. So the orbital and the spin are entangled. So they form a total J equal to 0. This is a simple atomic physics. So the on-site, if you only consider on-site spin orbital coupling, so the local moment will be J equal to 0. And the excited one will be J equal to 1 and J equal to 2. It's an entangled object of spin and orbitals. So they're separated by spin orbital coupling. So if that's enough, if this is the story, right? The local ground state is a J equals 0 ground state, then the story is over. There is nothing else. The magnetism is gone. Everything is non-interesting, right? So that's another story. The system has magnetism, right? The system has a tendency to magnetic order. So that's not the complete story, right? So the complete story is so this is the on-site spin orbital coupling, which favors spin orbital entangled singlet, If you put I was trying to make a broad. Let me go back to this letter. Yeah. What? Yeah. So there is a. Yeah. So there is a. So the physics are the follows. So there is a CV exchange interaction in addition to this spin orbital coupling. So the competition is due to the spin orbital coupling and exchange interaction. So exchange interaction would favor some kind of magnetism, of this sort, and the spin orbital coupling would favor a spin orbital singlet. So there is a competition between these two, and these two will give you this kind of phase diagram, just like what we derived earlier for the competition between single anisotropy and the spin orbital coupling. So that's the minimum model. Yeah. So what's interesting here is the competition is due to the spin orbital coupling. It's not due to single anisotropy. So how do we confirm? How do we predict? How do we confirm? There is a strong spin-orbital entanglement here. So there is a beautiful work, beautiful result by Feyye. So imagine if we apply magnetic field. If we apply magnetic field, if the system is in a spin-orbital singlet phase, no, if we apply magnetic field, originally these J equal to 1 states, J equal to 0 states, they are separated by energy gap, and this energy gap can be renormalized by superexchange interaction. The on-side gap will be lambda, but if you include a superexchange interaction, this gap will be renormalized. It becomes a smaller gap, and this excited states, called triplons, J equal 1 triplons, J equal 2 excitations, they will have dispersion. They will have a band, and the gap between J equal 0 and this excited band. But if you apply field, you will bring some of this excited band down. You bring them down. Eventually, when this excited band is being brought down and touch the zero energy band, there will be a level crossing. That's where quantum phase transition happens. So you can apply field to drive the system from a spin-orbital singlet state to a magnetic order. So you can do that by magnetic field. So this is pretty cool. You can do that, and you can. This is the magnetic field. You can do that. So it turns out there is a two phase transition. You first you apply field. You bring this J equal to 1 states down, J equal to 1 band down. There is a level crossing. You get a quantum phase transition. So this is called a triplon. It's like a triplon boson-Einstein condensation. It's a boson-Einstein condensation with these triplon excitations. Those triplon mode is being brought down, and you get a boson-Einstein condensation, just like people do in ultra-cold atoms. So they are using real bosonic atom. So they put this real bosonic atom in an optical trap, in a harmonic trap, and they cool them, at very, very low temperatures. Then will condense by themselves. Here, what we do is we use an external magnetic field. We use external magnetic field. Maybe this is better. Yeah. So this is J equal to 1, J equal to 0. Apply field. We use external magnetic field to bring these states down, and there is level crossing. So the interesting part is so there is actual J equal to 2 states. If we apply field, this J equal to 2 states is also being brought down. Not just this J equal to 1 states. So there will be, two transitions. So if you apply field further, the system goes back to this spin-orbital singlet. And if you apply field even further, this J equal to 1 state is being brought down, and then you drive the system to a phase transition again. So there is a two-level crossings. The one happens here due to the bringing of this J equal to 1 triplons down, and then you brought this J equal to 2 quintuple turns down, and there is another level crossing. You get another phase transition. So in the magnetization measurement,
I think for the first level crossing, it has been studied by Mott 10 years ago for the diamond material.
It's this guy.
This one,
Yeah. I mean, in terms of field theory, it will be similar, right? Mm-hmm. But the physics is different, right? The microscopic degrees of freedom and the interaction that realize this kind of criticality or phase transition is completely different, right? Yeah. So this is the the structure, the rich structure on the magnetic field, is intimately connected to the spin-orbital entanglement structure of the local moment. So there is a strong connection between the measurement, the re-entrant phase transition, re-entrant phase transition, and the spin-orbital entangled local moment structure. Right. So here we actually make a comparison between different systems. So this is our system. There are two phase transitions, and indicated by the bump behavior in the transverse component of magnetization. So when the system occurs into a magnetic order, So the system developed a transverse component magnetic order. That's a boson-Einstein condensation of the triplons. So you can compare this with the spin 1/2 dimers. For spin 1/2 dimers, so this is called dimerized materials, where these each side is a spin 1/2 degrees of freedom. So this bold bond, this bold link, the interaction on the bold link is much stronger than the interaction on the dashed link. So in the beginning, one need to consider the interaction between on this bond. So this favor total moment equal to 0 singlet, right? Yeah. So this favor a total moment equal to 0 as total equal to 0 singlet, and the local or this for this bond, the excited state would be S total equal to 1 triplet, right? So if you apply magnetic field, this triplet will split, and eventually this triplet will touch down to this singlet. There is a level crossing, and this is called the triplon condensation. So originally proposed in this context, and there is only one triplon condensation because the local moment structure is organized by S total equal to 0 and S total equal to 1. So this is different from on-side J equal to 0, on-side total moment, total spin orbit entangled local moment J equal to 0 and J equal to 1, J equal to 2. So there is only J equal to 0, S equal to 0, S equal to 1, and this is brought down, and there is a quantum phase transition. So this is different from his. So this is probably more similar to the spin 1 dimer, where the degrees of freedom here is the spin 1 local moment. So they form S total equal to 0, S total equal to 1, and S total equal to 2. So when you apply field, this S total equal to 2 also brought down. So there will be 2 transitions. So our case is a little bit more analogous to S equal to 1 dimer rather than S equal to 1/2 dimer. There's another dimer that is, which is also due to EG orbital degeneracy. So if you apply field, there's no phase transition at all. The gap actually goes, this gap becomes larger as you increase the field. So there's no level crossing. Yeah. So this is quite nice. So another consequence is this correspondence between different electron configurations. So all these works are based on some simple observations. How you make a simple observation, try to abstract the problem, try to think about the consequence. So these are the first. The upper panel is the correspondence between the D8 electron configuration in a tetrahedral environment and this D4 electron configuration in an octahedral environment. So over here, the EG is lower than T2G. The EG is completely filled. So then you can forget about the EGs. Only focus on the T2Gs. So the T2G is partially filled. So this is just like a T2G is partially filled in an octahedral environment with only 4 electrons. So there is a 1-to-1 correspondence between this guy and this guy, right? Similarly, there is a correspondence between D9 configuration and D5. You can make a list a little bit longer. So there is a excuse me. So there is a 1-to-1 correspondence between one and another, just by removing the EG shells. So this is like the physics of from this simple correspondence. One can realize the spin orbit coupled physics, such as the iridium, osmium, mossnite, in the context of 3-dimensional transition metal oxide. So maybe this is trivial, but that lead to some very interesting consequence. Yeah. So the consequence is the spin activity was being proposed in the D4 electron configuration. If you dope this thing with electron holes, you induce a pure spin activity. So without much creativity, spin activity can be obtained in this fashion, in this system, in this nickel system, if you dope it, just by this correspondence. And only in 2014, we are exploring the spin orbit entangled physics in correlated matters. In correlated matter, mostly interested in these 4D, 5D transition metals, where the correlation meets the topology, meets spin orbit coupling. There are many interesting phases, such as ketone materials, such as white semi metals, such as various topological phases. So so this physics can potentially be realized in 3D transition metal oxides. Yeah. So finally, let me summarize. So we made some based on some observation from this simple compound that motivates from topological quantum paramagnet. So the suggestion is this is probably not a topological paramagnet, but the physics can be interesting. First of all, there can be this infinite number of excitation degeneracies due to frustration. There can be also this spin-orbital coupler correlated physics in 3D transition metal. So yeah, let me just stop. Yeah, thanks.
All right, thank you.